In my previous lecture, I talked about in Newton's Principia his proposition 1, theorem 1, and then his proposition 2, theorem 2. In this lecture, as I mentioned then, I'm going to talk about his proposition 4, which is on page 291 of A Student's Guide Through the Great Physics Texts, Volume 2. I'm going to talk about proposition 4 and the corollaries that are immediately after that proposition. Again, I think I should give you a heads up at this point that this is a little bit more mathematical. After all, this is Newton's mathematical principles of natural philosophy, so we shouldn't be surprised that he engages in some more serious mathematics. But this is going to be a little bit of necessary work, things that we have to do really to understand how he develops his theory of gravity. Remember, Newton is trying to be very rigorous in how he arrives at his theory of gravity. Okay? And also, maybe I'll say this at this point, the lab we're going to be doing this week is related to the corollaries in this proposition 4. So proposition 4 and the corollaries is a subject matter for the force and rotation lab that we'll be doing this week. So our reference is Newton's Principia, book 1, section 2, and this is proposition 4, and this is in my student's guide, page 291. Okay, so here is what Newton is going to try to do. I'm not going to follow exactly what he does directly. I'm going to do a little bit of a different proof, but I think this will be a little bit more transparent. So in this proof, what Newton wants you to do is he wants you to consider two objects that are both moving in a circular orbit. So consider two objects or bodies that are moving around different circles at constant but perhaps different speeds. Okay, so I'm going to draw a picture of this. Imagine that you've got one of the objects moving around this circle and another object moving around this circle. So one's a big circle, one's a small circle. And this big circle has a radius r. And let's suppose that during some time interval, delta t, that object moves from here to here, so it moves through some arc length right there, okay? And then this other body, it's moving around a circle also. It's going at a constant speed, just like this one. And during that same time interval, so the same time interval, delta t, it moves through an arc like this. Okay, so these have different radii and they're different arcs. I'm using capital letters for this object and small letters for this object. Okay, so this is object 1 and object 2. Now, what Newton is going to argue in this proposition is that in order to be held in orbit around this circle, you need to have a centripetal force acting on this one, right? So you're going to need to have a centripetal force always pulling in on this one. And you're also going to need to have a centripetal force pulling in on this one, right? That's what keeps it going in an orbit. If there was no force, this object would just move in a straight line. So the force is what keeps it moving in the orbit. And what he's going to argue is that these two forces required are going to be different forces, but they're going to be related to one another. In particular, he's going to say that the centripetal force required to hold this body in orbit is to the centripetal force required to hold this body in orbit in a certain ratio. What is that ratio? He argues, this is what he's going to try to prove, that it's equal to the ratio, I'm just going to write this out, the arc length squared divided by the radius of the big circle in the numerator, and here the arc length of this one squared divided by the radius of this circle. This is one of the claims that he's making in this proposition. So this is claim 1. That in order for these two objects to be orbiting, they experience centripetal forces. And so I guess maybe I'll call this claim 2. I'm going to order these differently. Claim 1, I guess I already said this. Claim 1 is that there must be a centripetal force. A centripetal force. And claim 2 is that in these two objects, the centripetal forces are related by this formula. That is what his proposition 4 is saying. That if you have two objects orbiting like this, there must be centripetal force acting on both of them, and the centripetal forces are in this ratio. Okay? So that's the claim. Now let's go ahead and see how he demonstrates or how he proves each of these claims. So first of all, let's do them in the order of claim 1 and then claim 2. So proof of claim 1. Well, here's how he argues. He says, if you're thinking about an object going around in a circle, and they're each going at constant speeds, since the speed is constant, that is, it's not kind of speeding up and slowing down and speeding up and slowing down. Since the speed is constant, that implies that equal areas are swept out by the radius drawn from the center to the object in equal times. After all, if during the first second it sweeps out a certain area, during the second second it's going to sweep out the same area, during the third second it's going to sweep out the same area, during the fourth second it's going to sweep out the same area, and that's all because it's moving at a constant speed. Okay? So equal areas are swept out in equal times, and then we know immediately there must be a centripetal force. Be a centripetal force, and we know this by the proposition that we proved in our last lecture, proposition 2 or theorem 2, right? Proposition 2, theorem 2 said if an object is moving in a curve and equal areas are swept out in equal times, then there must be a centripetal force. So there we have it. Claim 1 is correct. There must be a centripetal force acting on this object. Okay, that was a pretty easy one. All we had to do was invoke proposition 2, theorem 2. All right, now let's look at his proof of claim 2. This one is harder. Proof of claim 2. Remember, our claim 2 is that not only that there is a centripetal force acting on this body and this body, but they have this particular relationship between them. So how is he going to go about demonstrating this? And I'll tell you what, I'm going to get rid of this for now. I'm going to draw a couple of more pictures. You know what? Tell you what, I think what I'm going to do is I'm going to stop here and begin this in my next lecture, okay? Because it's going to take a little bit more time.